Okay, so I'd like to introduce our first speaker, Sebastian Geiger, to give a talk on his research work.
Well, good morning, everyone. While the slides come up here, just want to reiterate what my fellow chairs have said. Yes, it's really nice to be back in person, see everyone in person again. There have been two important events since I last stood up here on the on the stage and spoken about my research. Last time I was up here, I was wearing a very scruffy trainer jacket because I'd just broken several bones in my shoulder. And at the chair dinner, I had to ask some of the fellow chairs to cut my food. So I'm happy to report, can dress up again. The dinner on Monday evening, I could cut my own food. The other big news for me over the last 3 years was, like Arne, I've changed teams in the transfer window for energy simulation chairs. Now working at TU Delft, where together with Hadi, we are in the process of setting up the Energy Simulation Center for Geoenergy. So what I want to do, my plans for my future at TU Delft is to establish the chair for sustainable geoenergy within this Energy Simulation Center for Geoenergy. If I talk about geoenergy, this is a picture that a colleague of mine, Andreas Buschmeyer at Watt University, has produced. Geoenergy broadly refers to the subsurface, using the subsurface for non-hydrocarbon related energy. So talking about geothermal energy, one aspect, energy storage, so this could be thermal energy storage, CCS, compressed air storage, hydrogen storage, and to a certain degree, natural gas, which is a hydrocarbon, as a transition fuel during the energy transition. We try to model how those geoenergy applications work on the subsurface. We create reservoir models. You see a picture there on the bottom left. And what always surprises me with sort of a long background in geology, that's quite some time ago, is how simplistic at the end of the day our reservoir models are. So typical grid block in a reservoir model, and this is one of the models I've built with students in the past, 100 by 100 meters aerially, a few meters in thickness. We translate what this means in terms of rock and fluid mass. There's about 5,000 tons of fluids in that single grid block, about 50,000 tons of rock. And we assume that this rock and those fluids, they all have uniform properties. So they react the same way, they flow the same way. We go out in nature and we look at some outcrops and cores, outcrop analogs, and you see some pictures there. We see how heterogeneous multi-scale geology really is at the end of the day. And I've spoken, and students of mine have spoken at past summits here, how we can improve our reservoir models if we include this multi-scale geological heterogeneity appropriately and can make better forecasts about reservoir behavior. We can get easier history matches, we can assess uncertainties in a much nicer and much more robust way. With reservoir modeling, if you use standard tools, it's often slow and inefficient exercise and compromise. We can't get the things into the models we really would like to get. We also tend to lock in geological concepts very early in the modeling workflow. So we limit the way we explore geological uncertainties, how we explore different geological scenarios, different ways we think about the subsurface, different ways we interpret data sets. And again, we've spoken about this in past summits. Generally, if you look at the picture at the left, these reservoirs are a poor representation of the reservoir system, and we tend to emphasize matching models against production data rather than learning from models of how the fluids move in the subsurface. We tend to underestimate uncertainty, and because we have big computers these days, we tend to build very big models that are precisely wrong, they're not approximately right. Quite often we end up with two things we don't understand: the subsurface reservoir and the big model that you're trying to run on a computer. So in the research that I've been doing over the last decade and more with our students, what we try to do is we try to develop and apply some really agile new workflows that allow us to design good reservoir models that integrate geoscience and reservoir engineering for geoenergy applications in a much more effective way, in a much more intuitive way. So one of the big aims that I have at TU Delft is to establish what it's currently placeholder, the GETS Energy Lab. GETS stands for the Geoscience Digital Twin for Subsurface Energy. As I said, it's just a placeholder. And what we envision to doing there is to create a hub that brings together the various strands of research at the Department of Geoscience Engineering at TU Delft. We've gotten some really nice startup funding from the Delft Excellence Initiative to support these activities. So at the department, there's a group that does some fantastic work on subsurface imaging. They're developing new algorithms that help us to tease more data out of subsurface seismics. A lot of work done in partnership with industry. Together with colleagues from University of Calgary and Imperial College London for the past 8 years, we've developed the Rapid Reservoir Modeling Framework, an open source framework to very intuitively design reservoir models from sparse data. We're interested in learning more about RM, actually trying out RM. I encourage you to go and see Kylie Baird's poster, who shows how you use RM for geothermal applications. Hardy, together with Dennis Voskov, they have set up the Delft Advanced Reservoir Simulation Group at the department, and one of the projects they developed is the Delft Advanced Research Terra Simulator, an open source reservoir simulator that allows us to sort of test new prototypes, test new concepts, develop new concepts, new algorithms in an open source environment. We've recently linked RM to speak to Darts. We can run RM models directly in Darts. And Dennis gave a really nice introduction, really nice overview. I don't know where Dennis is sitting on, so closed loop reservoir management, data assimilation. There's a strong history at the department in closed loop reservoir management. And we want to bring that part into that GETS Energy Lab framework and this collaborative hub as well. Now, digital twins are only as good as the data, and there's a lot of data that we have, and there's a lot of really nice work being done by colleagues like Auka Barnhorn and others who work in the lab and actually creating data, input data for reservoir models, understanding some of the fundamental physics, very much along the lines that Giovanni talked yesterday about the fracture mechanics. And what really excites me is that at TU Delft, we are about to drill 2 deep geothermal wells, 3 kilometers deep on campus for district heating for the city of Delft, for the campus, also thermal energy storage site. We've already drilled 3 monitoring wells. It's a huge research facility for geothermal energy right at the heart of the campus, right at the heart of the city of Delft. And that project is led by Phil Warden. And this is sort of a natural first hub to try to bring out these different aspects of research that we have at our department. And ultimately, what we like to achieve is to bring this all into virtual environments. You can use this as a communication tool and communicate what subsurface science, geoenergy is all about to the non-technical stakeholders, because if society is not in our way, don't get the support of society for geothermal development, hydrogen storage, etc., then all the technical solutions that we come up with, they're not going to be successful, not going to be implemented. So coming to the technical parts of my talk, what I want to talk about is some work that really Alfredo Freitas, a PhD student, started with me at Harvard University. I'm still supervising him. I think he's online, has done for his PhD, so all credit go to him. And what Alfredo has worked on is to try to see if we can decipher fracture properties using well testing data in combination with machine learning. And as a caveat and as a disclaimer, so the machine learning that we are using is much more pedestrian, as the really nice work that Benham showed yesterday in his presentation. So why do we care about fractures? Fractures are ubiquitous in the subsurface. Some of the big geothermal aquifers that are targeted in Central Europe are fractured carbonate aquifers. And the fractures can create preferential flow paths that cause early breakthrough and bypassing of large reservoir volumes. We think of a reservoir modeling context. Brian Berkowitz stated quite some time ago that fractures often do not possess any homogenization scale. So strictly speaking, REV cannot be defined. If we build reservoir models, we always assume that we can homogenize, we can average out properties at the scale of a reservoir grid block, which is really difficult to do in the situation of fractured reservoirs. So the things we want to know if we deal with fractured reservoirs is where and when do fractures impact flow. And again, we've seen some work from Giovanni yesterday, from Leonardo yesterday, that tackle that issue. We also want to know what the effective properties of the fractures and the rock matrix are and how we can represent them best in reservoir models given the limitations of reservoir models that we have today. How much energy, for example, heat, is left behind in the rock matrix, because that's where the big volume of storage is for thermal energy, or if you want to store CO2 in the subsurface, how much CO2 we can store in the rock matrix. The fractures are just a tiny volume of the subsurface. We cannot change geology, so what we need to do is we need to think about how we adapt our reservoir engineering to minimize risk, maximize opportunities if we deal with fractured reservoirs. And again, in past energy simulation summits, students have presented work we've done around geological well testing. The fundamental difference here is we're not using analytical solutions, type curves to look at well tests. We go to the outcrop, we look at fractured reservoir analogs, we use image logs to get an idea of the subsurface, we build conceptual models of the subsurface, we represent the fractures explicitly in our reservoir models, and so sector scale models that are built around single wells. We then simulate drawdown curves and build-up curves, so pressure tests. Using these models, we create synthetic pressure responses, and we compare these synthetic pressure responses to well test data. And if they don't agree with each other, then something is wrong in our understanding of the fracture geometries of the subsurface models. We update the models, we update the fracture properties, we rerun the simulations until the well test and simulations agree. And the idea is that we understand some of the key reservoir architectures, the key fracture properties that influence subsurface fluid flow. And what we have shown, this is data here from a real reservoir, it's a virgin carbonate reservoir in the North Sea, that you can really learn a lot with very limited subsurface data from that approach. So this well test that we reinterpreted for an operator, what we could demonstrate that high conductivity fractures in the subsurface are drained first. Then you have an initial recharge from a high permeability rock matrix. And then later on, there's a second fracture network with lower conductivity fractures and a lower permeability matrix that provides additional recharge of the fractures that are depleted first. We also had some mini DST data for that same reservoir, and Alfredo worked on this. So mini DST are something tiny reservoir intervals with very tiny fluid volumes, very short time scales. And what Alfredo showed is that for this particular reservoir, in this particular formation, it appears that the spacing of these high conductive fractures is roughly 1 fracture every 8 meters. And the low conductivity fracture, the secondary fracture networks appears to be, the first fractures appear to be located distance approximately 25 meters away from the well. And what really struck us when we did this work is how unique the answers are. So if you change fracture intensity, fracture properties, you couldn't get then the well test to agree with the fracture data unless you changed something fundamentally in your geological assumptions, which was not consistent with the existing data. So that got us thinking and forms of part of Alfredo's PhD thesis. And our hypothesis was, can we detect fracture properties systematically from well test signals for a widely varying set of fracture statistics? So what Alfredo set out is he wrote his own little discrete fracture network generator and used some input data from outcrop analogs, and Kevin Bistam's PhD thesis several years ago at TU Delft was a great source of inspiration for us. And he created geological sound fracture networks using that approach. So he created over 2,500 discrete fracture networks. For each of these 2,500 fracture networks, he then created a grid, he mapped these fractures onto the grid and ran a well test simulation. So every simulation, all the fractures represented explicitly, and he simulated a drawdown curve for these 2,500 fracture models. Did a lot of validation to ensure that the simulations are free from numerical artifacts, etc. And then he used clustering, machine learning technique to cluster the pressure derivative curves, identify trends, identify reference and representative samples of the pressure derivatives that then link to representative fracture networks, network geometries, network characteristics using clustering techniques. I'm going to talk you through each of these individual steps now in a bit more detail. So to create the fracture networks, we used probability density functions for the fracture length and the fracture intensity to then stochastically generate these 2,500 individual fracture networks. And you see just 3 different fracture networks below. And we created for each of the fracture networks, we created multiple realizations as well. So we had these, in total, we had 2,560 different geologically constrained fracture networks. And each of these fracture networks were mapped onto a simulation grid that was very refined, high resolution grid. So the fractures are modeled explicitly on the simulation grid, and then around the wellbore, there was additional grid refinement to make sure that the simulation results which we use to generate these synthetic drawdown curves, that we are free from numerical artifacts. And we did some smoothing to the resulting pressure curves because there was a bit of oscillations at early time that could upset the clustering algorithm. So we did some additional smoothing, running moving average over the curves to take out some of these oscillations in the pressure data. So what we ended up with a data set of 2,560 individual synthetic drawdown curves for each of these 2,560 fracture network geometries. And then we started, or Alfredo, I must say, started clustering these drawdown curves. And what he did after a lot of work, he found out the best way to do this is that we use a second derivative of the drawdown curves and we normalize them using dynamic time warping. Problem with these drawdown curves is, depending on the fracture geometry, they have very different length scales. So we may have some very similar shapes in the drawdown curves, but one has a much compressed time scale, another one is a much longer time scale. What dynamic time warping does, it normalizes curves or temporal data. It normalizes temporal data. And there's a little animation here that shows the key idea. So you have these two figures that are moving, and one is moving faster than the other. And if you follow the movement of the limbs, they actually spread out in time. But if you normalize them, you actually see that the movement of the limbs are very similar. So with this dynamic time warping, you then see that you really can focus on the difference in the curves rather that are not produced by difference in curves being stretched over time. So using then the second derivatives, I've really used cluster the second derivatives using k-medoids methods. So k-medoids rather than k-means take a sample of the data sets and they measure the dissimilarities between the central data point shown here on the right with this orange square and all other data points within a single cluster. So don't focus on the average behavior, the mean behavior, but they look at the individual data points. We validated this approach using analytical solutions for different fracture geometry of well-test behavior, so radial homogeneous drawdowns all the way to radial composite drawdowns to porosity behaviors. Use an elbow method, and for this we know that we would get 4 different clusters out, and we used the elbow method. We got these 4 clusters out, and we did a confusion matrix to check that the predicted classes match the true classes and all work nicely. However, if you then shift the curve such that the offset in the curve is in the vertical direction, so it's the magnitude of the pressure drawdown, not a temporal change, less of a temporal change, the clustering struggles because the dynamic time warping and the pressure derivatives, they don't pick up easily these vertical offsets. So if you look at the confusion matrix for second test case, where the main difference on the vertical offsets, the magnitude of the pressure drawdown, we see that that we struggle to predict the right classes based on the true classes. So this is where the idea came into play to use the second pressure derivatives, and use that as a clustering techniques. And in this case, the true class and the predicted classes agreed again very nicely with each other. So for the full data set of over 2,500 curves, we found that we have 12 different clusters of pressure drawdown behavior. And what you see is for different window size or different ways you can set up this dynamic time warping algorithm, we always came up with these 12 different clusters. These are examples of the clustering of the drawdown curves. The first pressure derivatives, the thick black line, are the representative curve that is based on the clustering algorithm, represents best the total ensemble of curves identified or labeled within a certain cluster. And this is the same story for the second derivatives. We then started looking in the data in a little more detail, and I've really used multi-dimensional scaling of the second derivatives. And you see these 12 clusters here shown by different colors. And what is really interesting to see that 9 clusters follow very much along a narrow band of X values in the multi-dimensional scaling, and 3 clusters from clusters 10, 11, and 12 are offset at significantly different values in the multi-dimensional scaling. These clusters 10 to 12 These are the cases where the production well intercepts the fracture. Clusters 1 to 9, a situation well is located in the matrix, close to, but not intercepting any fractures in the fracture network. We then did is with these 12 different clusters that we identified, we looked then at the input parameters and assign that belong to the individual fractures. So the fracture average fracture length, the average fracture aperture, fracture intensity, the distance from the wellbore to the closest fracture, and the fracture connectivity, and looked at and tried to analyze how do these fracture properties, the characteristic of the fracture networks, influence the clustering behavior. For clusters 1 and 2, those are the cases where the lowest fracture connectivity and intensity. The derivatives, the representative derivatives for these situations, they're very similar to single porosity pressure drawdown behavior. So if you would only look at your pressure drawdown behavior, in those cases, you would not expect that a fracture is present because they look like classical well testing would interpret them as a single porosity behavior. But you have, in this case, you have a fracture enhanced matrix permeability. Fractures 3 to 9, they're all clearly influenced by the fractures, but the well still doesn't intercept the fractures. So if you have core, you wouldn't see that fractures are present. Initially, there's a radial flow signal, and then you all these clusters have a very negative second pressure derivative, and then they sort of trend upwards with a positive second pressure derivative. Fracture in clusters 3 and 4, the fractures have very similar length and similar connectivities, but there are variations due to the different connections between the fractures, the different locations between the fractures. And that's sort of typical if you have a poorly connected fracture network that is close to the percolation threshold. Clusters 5 and 6, the fractures really enhance the matrix permeability. And clusters 7 to 9, we have well-connected fracture networks that mask any obvious traditional flow regimes that you would expect for naturally fractured reservoir. Having said this, cluster 9, there are quite a few of mislabeled pressure derivative curves in there. So that's a cluster we trust least. Clusters 10 to 12, this is the cases where the well always intercepts a fracture. We have linear flow regimes for clusters 10 and 12. They relate to poorly connected fracture network. And clusters 12 corresponds to the best connected network, but again, only a single porosity flow regime, not a dual porosity flow regime. So hardly any of these 2,560 pressure derivatives showed any signals that we would typically expect for a naturally fractured reservoir. So to sum up, what Alfredo has done in his PhD, which is now slowly coming to an end, he's developed a new machine learning approach to classify pressure trends and behavior in naturally fractured reservoirs. We observed there's quite a huge variability in pressure transient curves that can be characterized to 12 unique clusters. And we call them reference curves, not type curves, because type curves are based on analytical solutions. These are based on geologically consistent fracture network geometries or reference curves. The key take-home message for us or for you is that classical dual porosity shapes are very, very rare. So if you rely on dual porosity shapes in well test signals, it's really easy to miss the presence of fracture. We've seen every drawdown behavior that you see in textbooks and some that you don't see in textbooks that are related to fracture networks. We also saw there's a very clear link between the reference curves and the fracture network's characteristics. So the distance between the well and the fracture network, the spatial arrangement of the fracture network, the first order control, properties like fracture connectivity, intensity, the length and the aperture of the fracture network, the fractures are second order controls. And what we are planning to do is, so the next step with funding from Energi simulations to expand this work to try and see if we can classify heat flow behaviors in fractured geothermal reservoirs in a very similar way. And I hope to report back on this at a future Energi simulation summit, hopefully without any broken bones at that occasion. So thank you very much, and I'm happy to take any questions.
Thank you, Sebastian. Any questions? There's no online questions yet. Any, Radu?
Thanks, Sebastian. Did you actually consider any horizontal fractures into the system?
No, so that I sort of skipped over. So we treated this as essentially a 2D system, so with layer-bound, bed-bound fractures, no horizontal wells. So this is really the first part. That was challenging enough to get this done. Horizontal wells, horizontal fractures would be so the next step, or deviated wells would be
Right.
the next step to look at. Yeah.
I understand. And about the stress anisotropy, I
Yeah.
think that's an important part that should be probably captured because some of them behave, some of them are actually, you probably reflected in the aperture a little bit, but
Yeah.
I think it would have an impact on the flowing ability if you have different anisotropies. I mean,
Yeah,
you increase
great
the
question. So what we did is we used a relatively simple scaling law to relate fracture aperture to fracture length. Next, another step, follow-up step would be to talk to people who know much more geomechanics, Giovanni and Rick, for example, and try to squeeze and stress the model, look at stress anisotropies, and then let fractures open, close under stress to see how that changes the behavior. So there's a lot of additional work. This is to get the workflow nailed down.
Thank you, Radu. Next question, please.
Hi, thank you for a really interesting presentation.
Thank you.
My name is Katja Sechkina. I'm from the University of Toronto. So I had a few questions. So my first question was, you had 3 fracture networks that you mapped. I wanted to ask, how did you develop these fracture networks?
Okay. So the 3 fracture networks that I've shown, there were just 3 examples. So in total, based on the input, we used a full factorial design over a range of input parameters, fracture intensities, average fracture apertures. So that created 256 different fracture, different parameters, which we can use to stochastically generate discrete fracture networks. Then each of these parameters, we ran the stochastic fracture network generator 10 times to account for variability in the stochastic process. So that's where you came up with 2,560 fracture networks in total with 256 different combinations of input parameters.
Okay, thank you. I also wanted to ask, so you mentioned you did some smoothing on your data on a moving average.
Yeah.
So I'm assuming that's probably a REMA, but I wanted to ask if you considered other things like moving median, and how did you decide what was the average period for smoothing the data?
So this is a really good question. This is something where I hope that Alfredo is online and can answer what exactly he did for the moving average part. We didn't test different ways. It was just the ways of at very early time, the first seconds of the data, versus some oscillation. You just want to get rid of these oscillations. Once you sort of at the minute to tens of minute time scales, those oscillations had disappeared. And I think it was just some running average in MATLAB, because that's what he used, but I need to double check with him what exactly used. I know we didn't play around with different averages, averaging methods. Yeah.
No, for sure. I was just wondering if you considered something like a Loa smoothing, but
no, that's definitely not.
One more question. You mentioned your data when you clustered it. You had 4 clusters. I wondered, where did this number come from?
So yeah, so seeing that the time started running faster and faster here. So this was the validation test. So we used 4 different analytical solutions. For radial flow, radial composite flow, dual porosity behavior, and 4th one. And for each of these 4 different analytical solutions with 4 different parameters that, thank you. Don't know if I can go back here. No. So radial homogeneous, dual porosity, vertical fracture, and radial composite system. So 4 different analytical solutions. For these 4 different analytical solutions, we used, in this case, 4 different input parameters to create just a simple pressure derivative, solving these equations analytically. And because we had 4 different solutions, we knew we would need to get 4 clusters back. Okay. And that worked really nicely with the first derivatives for the situations where the offset is mostly in time. The offset is in the magnitude of the pressure. So if you change input permeabilities, for example, then the clustering techniques struggle to identify these clusters until we went and took the second derivatives, which then focus more on the offset in time. So we knew that because we had 4 analytical, the short answer is because we had 4 analytical solutions, we knew we would need to get 4 clusters back.
Okay. So the clusters over the full time series. Okay, thank you so much.
Thank you.
So there are a few questions online from Zheng Wang. Thank you for your interesting talk. How did you map the natural fractures with various directions to the regular grid blocks?
Again, very good question. So this is where we, inverted commas, cheated a little bit, because we simply set up the fractures that there's no degree of fracture variation in the horizontal and the vertical direction. You could map it onto a standard Cartesian grid, rather than doing some work that Hardy is doing, Dennis are doing with embedded discrete fracture methods, PDFM, unstructured grids, which make it possible, but just make it even more complex to do this. So we just made sure that the fractures are always vertically arranged, then you can use Cartesian grids.
Okay. Next question is from Mark Jung. For machine learning algorithm, could you please comment more about model selection? What kinds of clustering algorithm are selected? What are the benefits? Thanks.
So we use the K-medoids algorithm and clustering algorithm. And let me just go back here. So we used K-medoids because we wanted to look at the individual data points that are being assigned to a cluster. So the right picture here, rather than K-means cluster, which looks at the mean or the average behavior of a set of data points in the clustering. We looked at some, the K-medoids has some initialization ways to initialize this, and so we look very carefully, well, we're free to look very carefully at the ways to initialize the K-medoids cluster and the parameters you can use in the clustering techniques to ensure that there's no, that then the artifacts in setting up the K-medoids cluster are limited in the selection approach. What I should point out, so because there are questions, so all this, we have written this up as a paper, is being submitted in due course, and then all the data, the input data, the scripts that we use to create the fracture networks and map the fracture networks onto the grids, etc. All this is going to be open access. If you want to play around with the data set and the scripts, you're more than welcome to.
Great. One last question here online from Kasha Kari. Thank you for your presentation. Is it possible to reach to the conclusion that, that which parameters are playing the most important role in your models globally?
Yeah, so the biggest, or the single biggest one is how close are your wells, what is the distance between your well and the nearest fracture? And that sort of is quite, in hindsight, perhaps not that big of a surprise, because, but it was something that surprised us initially, that things like fracture intensity or fracture aperture, fracture permeability are secondary controls. So the single biggest parameter of influence was how close is your well to the nearest fracture.
Great. Okay, once again, thank you, Dr. Geiger.
Thank you very much.
Next.